Hello, my name is Sophie Baker, and this is a pre-recorded presentation for the 2020 meeting of the Society for Mathematical Psychology. And today I'd like to talk to you about degenerate optimal boundaries for multiple alternative decision making. So first we'll go through the conventional two-choice model from which we'll build our multiple choice model later on. So this is an integration to threshold model. So evidence is accumulated to a threshold, and once the accumulator passes that threshold, a decision has been made. So per trial or per choice, there's a single accumulator where the sign represents the alternative in favour. So for example, this child choosing between a snack, either a cake or an apple. If the accumulator is positive, so between 0 and 10 on this scale, they're in favour of cake, but they haven't made that decision until the overall evidence reaches the threshold. Upon crossing the threshold, an error is generated, so is that the right choice or not, and a decision time. A few things to note: the accumulator isn't normalized, and the thresholds in this model are conventionally single-valued and constant over time, although this is currently debated, which we'll get into in a couple of slides' time. This model is well supported, both with behavioural and neural evidence, so reaction time distributions and neural recordings are well matched by the model. So decision making. So a hot topic in the field with respect to these integration to threshold models is whether or not there is time complexity, so if there are temporal dynamics, particularly with respect to collapsing thresholds, so whether thresholds reduce over time and how this relates to apparent urgency signals that have been recorded in places like area LIP. Importantly, there's no consensus, so top right you can see a couple of reviews posing the question as to whether or not the evidence is better represented by models with or without these temporal dynamics, no consensus. And bottom left you can see that there's also a growing body of work towards multiple choice results, of which there is no normative model yet and which remains underdeveloped as part of the field, which is something we're hoping to address in this talk. So we're interested in multiple choices, and within that scope, what evidence accumulation looks like for n choices, because it's not necessarily obvious, what optimal thresholds look like within this framework, and an explanation for the dynamics that we pointed to in the previous slides. And what did we find? So first, the framework that we use. So the integration to threshold models for two choices come in the form of the SPRT and the DDN, the drift diffusion model. So the SPRT is a ratio of sequential Bayesian inference per choice, and that gives you a single accumulator with positive and negative values representing each alternative. And then the drift diffusion model represents evidence accumulation for two choices as a particle diffusing in 1D. So what we can do to extend this to multiple choices is to deconstruct the SPRT into sequential Bayesian inference per choice, and that's what you can see on the left. So this is an example for three choices. And you can see that we've deconstructed and we've just used sequential Bayesian inference, and that gives us a belief or a posterior probability per alternative, so H0, H1 and H2, and we have accumulators per alternative, so it's a normalized space. Within this representation, you can see the dashed line, the threshold, is constant valued or could have some temporal complexity, but that's kind of the extent of it. What makes this more interesting is if we then apply the concept of the drift diffusion model by using the posterior probabilities as belief values and using those as spatial coordinates to map a decision trajectory of the belief distribution across the choices in the space. So on the right, you can see the axes are now those posterior probabilities, those beliefs, and the decision trajectories evolving in space. So color matching from the left to the right, that yellow is exactly the same trajectory as you can see evolving on the right. The thresholds, the dashed lines, are completely equivalent to those on the left. However, we've now gone from one accumulator per choice, so 3 accumulators in total, to one multidimensional accumulator. This has some really interesting geometrical consequences. So we find that the trajectories are evolving in ND, so for 3 choices in 3D, but they are constrained to an n-1D simplex, so a 2D simplex. In this case, it's a triangular plane. But where it gets really interesting is that the decision thresholds gain dimensions as well. So the decision thresholds become n-2 dimensional. In this case, a line, 1-dimensional. Because we're using sequential Bayesian inference and then using those values as spatial coordinates, this extends naturally to n alternatives. For example, 4 choices, We have 4 accumulators on the left, and this can be represented in a 4D simplex, which is a 3D tetrahedron shown on the right, where the 4th dimension goes into the page, and the decision thresholds, you can see these dark triangles, are planes. And so you can imagine that these could be very complex. So the question is, what shape should these thresholds take? To explore the character of multiple alternative decision thresholds, we choose 3 exploratory parameterizations, curve power oscillatory, and use a maximum of 3 tuning parameters, so theta, alpha, beta, for tractability when we optimize later. So these are as compared to the flat boundary on the left, which is the conventional 2-choice equivalent in this framework, and these parameterizations were chosen as the minimally complex increasing. So we want to optimize these extend naturally again to n dimensions. So what happens when we optimize these parameters? Spoil it in the title, we find that they are degenerate. So we use stochastic optimization and explicitly produce reward landscape before extracting the maximum. So we're maximizing for average reward, which is a weighted sum of error and decision time. So we were expecting to find either point maxima or something that looks like a convergence to a point maxima. And instead what we found was that maxima were areas. So these are degenerate sets of optimal parameters, so they are degenerate sets of optimal decision thresholds. So some good questions following this. Firstly, are they actually optimal? And we tested this by generating SAT curves, so speed accuracy trade-off curves, for the all set of optimized parameters, and found that they produce smooth, coherent SAT curves, and that the curves produced by the optimized parameterizations were the same on average, so they were consistent. We also checked that the decision thresholds were qualitatively different, so they weren't small variations on the same shape, they were qualitatively different, and we found that each of them included the flat parameterization. So the 2-choice result of single value thresholds existed within that optimized set. Analyzing these SAT curves, we found a second type of degeneracy, which was a degeneracy of speed accuracy trade-off with the same maximized average reward. And there are a couple of reasons that this might happen. One of which is that the base risk, the reward calculation, is under constraint, but also that different combinations of average error and average decision time give you the same average reward, which would result in variations of speed accuracy trade-offs. So we looked at how threshold parameters changed with speed accuracy trade-off. So this example shows 3 particular cost ratios, which give 3 different maximized values of average reward. For each set of optimized decision threshold for a given cost ratio, there is a degenerate set of speed accuracy trade-off values. So for example, the top left reward landscape matches with A in the bottom left figure, and you can see that optimized set spans a range of speed accuracy trade-off, but all of which give the same maximized mean reward. So the next question is, so we asked whether or not there were dominant parameters that dictated the speed accuracy trade-off produced. We plotted the SAT colored by the different thresholds, so theta, alpha, to see how those thresholds changed along the line. And you can see that for theta, it's consistent that theta decreases as you move down the curve. However, for alpha, the amplitude parameter, had no clear correlation with SAT. So how does this link in with the debate around temporal dynamics for 2-choice decision thresholds and recent findings with respect to urgency signals? Well, a unique characteristic of multiple choice decision thresholds within this framework is that mean decision time changes across the decision plane. So this is our 3-choice decision plane, as an example, coloured by mean decision time. And you can see that if you look, for example, at the dark blue line on the far left, if the decision trajectory crosses the blue line in the centre, you have a lower decision time, and if you cross the threshold near the edge, you have a higher decision time. So as you move along the threshold, your average decision time will change. And so there's some relationship between the value of the threshold as you cross it and the decision time. This is also a good illustration of the qualitative differences that we found in our optimized set. So all of these example thresholds, we have curve on the left, power in the middle, asymmetry on the right, are all optimal with respect to maximizing to the same average reward. So we can transform these decision thresholds to compare with two choice results and plot average threshold value over the time at which a decision is made. And that gives us these implicit dynamics. So these are still stationary thresholds, they're all within the optimized set for its parameterization. However, we uncover things that look like dynamics. So you can see each row is a differently categorized type of dynamic, so increasing, decreasing, flat, and then each row is the parameterization, curve, power, symmetry, and therefore those three different cost ratios that we looked at in our reward landscapes. These implicit dynamics support increasing thresholds, collapsing thresholds like we saw in the review slide at the beginning, as well as the conventional constant valued flat thresholds. So it's quite striking that you can see what look like temporal dynamics whose origin is in complex spatial decision thresholds. How does this fit together with behavioural data? Well, we found that this framework replicates other well-known decision behaviours. So purely as a result of using a normalised space, so using the posterior probabilities as our decision coordinates, we can replicate the violation of independence of irrelevant alternatives, the violation of the regularity principle. We find that our decision thresholds satisfy Hicks' law, this first panel on the left, and that it satisfies speed accuracy, offset, and slope, so shown there on the right, as number of choices increases. Our conclusions, so insights and implication. Our framework implies that the brain performs Bayesian inference directly versus an implicit use for reward estimation. We uncovered a hierarchy of mechanisms for optimality, so we found that inference, so sequential Bayesian inference, had more impact with respect to making optimal choices than normalization, so using those posterior probabilities directly, which it then had more impact on optimizing decisions than boundary shape. And we argue that this hierarchy is advantageous for generalization and learning because it means that there's far less emphasis on learning the precise form of decision boundaries in order to make decisions well versus the mechanism that's being used. An implication from our implicit dynamics is an alternative explanation for the origin of urgency signals recorded in the brain during decision tasks, that these may be an artifact of using complex decision rules as opposed to a true urgency signal, and so informs the debate around collapsing thresholds and urgency signals. And then degeneracy, why should it be the case that decision thresholds are degenerate? Again, it eliminates the need to learn precise boundary shape, so optimality in decision making becomes more heuristic, and less sampling would be required to adapt to novel tasks. Some predictions from our work. So we predict that mean offsets would be independent of changes of the task. So changes in reward rate or the speed accuracy trade-off required wouldn't change the mean offsets because they're purely due to the priors decreasing with n's. Second prediction, neural population activity should be near an n-1 dimensional subspace, so are simplices during evidence accumulation, and that this manifold might vary from subject to subject or trial to trial while maintaining optimal performance, and that variability among individuals may depend on the particular form of degenerate threshold they're using. And finally, we predict that dynamic signals may exist on two timescales, or at least be read as such, but we might see temporal dynamics on a faster timescale for implicit dynamics, so those that look perhaps like urgency signals, but are due to complex decision rules, and on a slower timescale for explicit threshold dynamics. So where there are truly collapsing thresholds, for example, that would happen on a slower timescale and be more consistent from trial to trial. Many thanks to my supervisor, Nathan Lapora, and Tom Griffith, whose discussions were much valued, and to all of these people at the bottom for helping fund us. And thank you all for listening. This is me, and any more questions you can contact me at the address at the top left there.